Hey everybody, thank you for coming tonight. Sorry for the late email that we sent out. If someone is not on the sign-up list who's here tonight and you want to be on the sign-up list, just give us a shout in the chat box and we can give you the link so that you're always on it. I don't know if any of you have been forwarded the link, but there's a sign-up so you can get on our list so you have it every week. So tonight the plan is word problems, and word problems for anyone who's been in our curriculum is kind of a smorgasbord of different topics. And you know, we actually call word problems, we use the term word translations a lot. The reason we do that is because you know, really what you're doing in a word problem is you're taking words, you're translating them into math equations, and then you're getting back to the kind of comfortable place that is algebra. So anyone who's going to be successful at word translations or word problems is going to be able to successfully take what you're reading and put it into math. Now, for some of you who have, you know, read other guides and done other courses may hear a lot about back solving and things like that. You know, between Scott and myself, we feel like the best way to deal with a word translation is to definitely attack it head on. Back solving can work, but we feel like it's pretty limited. So, you know, with that said, I want to get started tonight with a classic type of word problem, which is the age problem, and then we'll move into some other types, and then Scott will, of course, take over after that. So I'm going to give everyone about 2 minutes as you get your answer, put it into the chat box, and then we can go from there and go over it. So let me post it right now. Okay, great. was about 2 minutes there. So, there are some tricky things involved with doing age problems. And the key is always being very clear in what your variables are and what they represent. So this one's actually a little bit easier with paintings rather than actual people and ages. And we'll do one with people next. But the thing I would label is painting Y. I would say Y. And I'm going to say the age today. Obviously, paintings aren't necessarily ages. But for argument's sake, let's just say that. So that's Y's age today. Now, today is super important. You're going to see why in a moment. We're going to say variable Z is Z's age today. And then what we're going to do is start our equations. And we need to take these word for word, line for line. The first, and I would say of the easier equations, is painting Y is 4 times as old as painting Z. Now, one of the things I always teach my students is I tell them to always make sure your equations are very well balanced. Now, what that means is that you always need to take the smaller side and multiply it or add something to it to equal the larger side, assuming you're multiplying by an integer or a whole number. So when it says Y is 4 times as old as Z, what that means is that Y is actually the older painting. So we would take Z, which is the smaller or younger painting, multiply it by 4, and set it equal to Y. Now, this is dealing with the variables in today's terms, but you can see next it says 50 years from now, painting Y will be 3 times as old as painting Z. So what we do is we add 50 years to Z, because that's the age today being Z. And since it's the smaller of the two, we have to multiply it by 3, and that's going to equal painting Y, not painting Y today, but painting Y in 50 years. So notice I added the plus 50 to Y, and again, notice I added the plus 50 to Z. We distribute the 3, that gives us 3Z plus 150 equals Y plus 50. We bring the 50 over, so we have 3Z plus 100 equals Y. And now we're ready to basically finish our substitution here. And when we do that, we can plug 4Z in for Y here. And by doing that, do a little arrow here. Take this, we're going to plug this in for Y. This is going to give us 3Z plus 100 equals 4Z, or 100 equals Z. Notice we don't care about Z, we care about Y. So finally, we know that 4Z equals Y. 4 times 100 equals Y. 400 equals Y. Answer choice C. So for any of you who struggled with that or felt like, the translation was off, the good news is you can memorize all this. At the beginning, actually, of our word problems chapter, we have a whole chart full of word translations. Obviously, we use 3 or 4, I think 5, but you can continue those on your own sets of flashcards and things like that, as I did when I was a student. Anything I got wrong, I made sure that I put on a flashcard, I memorized why it was wrong, etc. So you can easily do this with word translations. So with that said, I want everyone to start this here, and we'll do 2 minutes. Oh, sorry, everyone. I was just talking on mute. So what I was saying is that we're given the things in a backwards order. And you'll notice that the age 8 years ago is given first, whereas the age in present day is given second. So we're going to start with the green equation because it's easier. But the variables, instead of using two J variables and J with a subscript, which I don't really like, what we're doing is we're going to say F for the female, that's Julie, it's today's age. M is James, he's the male, and that's today's age. So the first equation is F is 6 plus M. That's because Julie is older by 6 years. We're adding to, of course, the lesser age, which is James. And then it's saying 8 years ago. So we have to subtract 8 years from Julie's age. And she's 4 times as old, so she's the older one. So we're taking James, who's younger, subtracting 8. And then we're just simplifying. And remember, before you plug, always make sure to simplify, because if you don't, you're going to be dealing with messier stuff, and you don't want to deal with anything all that messy, at least in my opinion. So you want to make this as clean as possible and then sub in. The other thing, too, is make sure you're not taking the first equation you wrote and using it in the second equation. Make the equations independent of each other and then do your subbing. So if we bring the 8 over here, this gives us F equals 4M minus 24. Now we're ready to sub in. We take 6 plus M, put it in for F. 6 plus M equals 4M minus 24. Add the 24 over, bring the M over here. This is going to give us 30 equals 3M. M, of course, equals 10. That is James's age. We want to know Julie. She's 6 years older, so she is 16. Remember, 10 is an answer there. 10 would be a trap, so always make sure you're solving for exactly what they're asking for. Okay, so those are a couple of age problems. We could do those all night, of course, but as we like to do in our webinars, we want to kind of spread the love here to some different things. So I think another great type of problem is, well, I will just put it up. We have a name for it, but they're actually pretty hard to describe. But nonetheless, they are fantastic problems. So we are going to do this guy here and probably follow that up with a data sufficiency question as well. I'll give everyone 2 minutes to do this. Okay, so that was about 2 minutes. You know, as I said, these questions are hard to describe as far as giving them a label, but they are very high impact questions that the GMAT definitely likes to test on. And they're great because what they're testing is this idea, do you know how to deal with something where they say, you know, each additional day thereafter, and they say it again for each additional day thereafter here. Now you'll notice there's only one variable that is going to be used here, and this is going to be, we could say T for total days, regardless of company, because what's happening is we're ultimately setting these equal to each other. So I'll just put company A on the left, company B on the right. And here's what we notice. We notice that to rent a car, company A is $50. So already we know there's a charge of $50. And then it's saying $40 per day for each additional day. So what we do is we're not multiplying 40 just by T, which is a common mistake made, but we're minusing the first day out of that because you're not getting charged the $40 for the first day. So for instance, if you only rented the car for 1 day, it would be 50 plus 40 times 0, so it'd only be $50. Company B, however, is 35 for each of the first 2 days, so a grand total of $70. And then it's saying there's an amount for each day thereafter. That's going to be $50, but it's going to be T minus 2 now because we're not charged the $50 until the third day. So now it's just a matter of simplification. You know, always be careful when simplifying because this is where mistakes generally happen. So you distribute the 50. You can do some combining here. That's going to give you 10 plus 40t equals, and then the 70 with the minus 100. So that's 50t minus 30. We can bring the 30 over here. We can bring the 40 over here. It's 40 equals 10t. So 4 is equal to t, and that is our answer choice B. So a couple other things I want to get into here. I think doing a fraction word problem would be good. You know, if any of you are my students out there, you've probably seen some of these repetitions that we're going to do tonight, but these are all great problems. And again, for anyone using our curriculum, which I hope is, of course, everyone out there, we have so many different types of word problems in our word problems chapter. So some really high value stuff. So first fraction word problem I want to do is this right here, and we'll follow this up with one that's a little bit harder, but start with this here. Okay, so that was another 2 minutes. This is an interesting problem. There's a bunch of important components worth mentioning here. Something that's been brought up in past webinars, especially in ratios and percents. You know, the one thing that I've always told everyone is that if you have answer choices that are in fraction form, ratio form, or percentage form, or percent form, you can always plug in real values. So if you really, truly wanted to here, you could use a real number for a full cup of coffee. Now, do I think that you have to in all of these questions? No, I don't, but it is always an option depending on how, you work best. The other thing that's being tested here is the fact that there's always two sides to every fraction. So, for instance, if I said, I ate, 1/4 of the cake, you can easily say that 3/4 is remaining of that cake. Now, obviously, most of us do this in our head, but the reason that's the case is because we say 1 minus 1/4 is 3/4, and that's the math that's being done in our head. Now, certainly, I don't think on a GMAT you have to write out 1 minus 3/4 to see that 3/4 is remaining, but the one thing you always want to be aware of is that in these fraction questions, this is the type of thing that the GMAT is testing you on. Can you pick up on those different things? So if we clear the screen here, get started at this question, there's some interesting things. And I'm just going to use the variable. I'm going to say T is the full cup of coffee. So notice what they're saying here. And we've got the first hour he drinks 1/4. During the second hour, he drinks 2/3 of what remains of his remaining coffee. During the third hour, he drinks 3/5 of his remaining coffee. What fraction remains? So we don't really care about what he drinks. We continuously care about what remains. So what's great about this question is that there is a shortcut way to do it. Now, in our solution, in our chapter, we do show, the longer, more methodical way because everyone should know what this stems from. But the fact is that if we constantly care about what remains, when it says that he drinks 1/4 of his coffee in the first hour, well, we don't care about what he drinks. We care about what remains after that, and that's 3/4. And when he drinks another 2/3, we don't care about what he drinks. We care about what remains, so that's 1/3. And finally, he drinks 3/5, but again, we don't care about what remains. Or excuse me, we don't care about what he drinks. We care about what remains, and that's going to be 2/5. So if you do some canceling here, we see very quickly that we get 1/10 T, so 1/10 is actually what remains. So, the kind of final thing I can tell everyone here before, I pass things over to Scott is that, in any fraction word problem, they're going to be testing you on that. That's not going to be just some straightforward thing where you're just using the fractions they give you. A lot of times you're going to be bouncing back and forth. Now, the great news is that in our curriculum, you go to on target, you'll see that, we probably have 15 to 20 of these questions. So there's a ton of practice you can get. Like I said, anything you get wrong, use your flashcards, study them, etc. So Scott, I'm going to pass you the ball, and let's see how your mic is, and if all goes well, you'll take over.
Hey, Jeff.
Perfect.
Okay, good. Very good. Hey, everybody, good evening. As always, thanks a lot for coming. So what we're going to do here in the second half of the webinar is go through some different types of word problems. And, as I always say, for those of you who come regularly, there's one key thing that you have to do on the GMAT is you have to make things more simple. Because if you think about it, really with anything, and don't start this problem yet. Really with anything, you can make it more complex. But especially on GMAT or GRE problems, they give you the ability to read between the lines too much and to make things overly complex and to complicate them. You don't want to do that. You always want to enter a problem with the idea that as ugly as it may look, there is a very simple solution. Because on an overwhelmingly large amount of GMAT problems, there is a simple solution. You know what? We don't care about the ones that there are not, because they're at the 99.99 percentile, and they don't matter to anybody, literally to anybody, okay? So always strive for simplicity. So when you go into this problem, we'll take about 2.5 minutes. I want you to try and find the simplicity, find the simple structures that lie in here. Okay, let's take it away starting now. Okay, guys, that's a little over about 2 minutes and 45 seconds. So you need to be able to recognize the difference between what we refer to as linear growth and as exponential growth that we would call quadratic growth. Now, this problem is actually dealing with linear growth. So the big difference between these two is in linear growth, what you have is you have a constant amount that's added to some starting point across a number of different periods. In an exponential growth, you have a we sometimes say constant factor, or sometimes more clearly, we say a constant multiple that's multiplied across a number of different periods. And in the next problem, I'll show you exponential growth. But this one happens to be linear growth. And it's linear, and it's all in the language. And again, the good news about word problems is they have to say what they mean and mean what they say, which is a really refreshing thing, right? So it says an investment portfolio grew by the same amount each year. Well, as soon as something grows by the same amount each year, we're in linear growth land. Okay, we're dealing with linear growth. So let's just say that X is the constant growth amount. Okay, so each year this portfolio grows by X. Well, the simplest way to attack this is just to come up with a little table for ourselves. So we'll say we have an initial value, which is equal to $100. And let's now say, well, what's the value after year one? Well, the value after year one is simply going to be the starting $100 plus the constant growth amount. Now, we don't know what X is at the moment, but whatever it is, that's what we're going to have after year one. We're going to have our initial $100 plus we're going to have X more. So what's the amount after year two? Well, we're just going to add another X on. So this is 100 plus 2X. Right? After year three, it's 100, but we add on 3X. Year four, do it over here. Year four is 100 plus 4X. Right? Year five is 100 plus 5X. Year six, 100 plus 6X. Right? Just to check in and be sure we're all following. The reason why it's 100 plus 6X is you started with $100, and over 6 years, each year you got X. So at the end of the 6 years, you have 100 plus 6X. Year seven, after year seven, you have 100 plus 7X. And after year 8, you have 100 plus 8X. Okay, now it says, highlighted in blue, it says the value of the portfolio after year 8. So here's the value of the portfolio after year 8 was 5/4 of the value of the portfolio after year 5. Well, there's the value of the portfolio after year 5. So with this information, we can write a really simple equation, right? What we're going to say is we're going to decode this literally. We're going to say the value at the end of year 8, right, 100 plus 8X, is equal to 5/4 of the value after year 5. That gives us a really simple equation. Because we have that fraction 4, we don't like seeing that. We're going to immediately multiply every term in the equation by 4 to get rid of that. All right, that'll give us 400 plus 32X is equal to 500 plus 25X. Shuffle these terms around. We're going to get 7X is equal to 100, or X is equal to 100 over 7. And of course, the question is saying, which of the following is closest to, which is a key indicator that some estimation is in order here. So you can clearly see that 100 over 7, I don't know, it's about $14. It's not exact, but it's about $14. So let's go back up, scroll up, and we can see, look how far apart these answer choices are spread. I mean, we could have estimated like crazy at the end there, and we still would have got it right. So the answer is C. So the key thing to be looking out for is the rhetorical cues that will alert you to the fact that we have constant growth, which we call linear growth. Linear growth. Okay, so in the next problem, what we're going to do is try our hand a bit at some exponential growth. And as you read the stem, see if you can see what words, what rhetorical cues give away the fact that this guy is an exponential growth problem. Okay, let's try this guy, and let's start now. Okay, guys, that was a little over 2.5 minutes. So I think a lot of you were probably able to see here what made this an exponential growth problem. It says a colony of lily pads in a certain pond increases in number by a certain factor each day. Now, you could have the word factor, you could have the word multiple, but if you basically increase by a constant factor every day, that implies multiplication, right? That implies multiplication. And we'll see this more clearly as we start the problem, the solution. It says if the colony initially had 2 lily pads, but after 1 week had 256, by what constant factor did the colony increase each day? Okay, so as we did with the linear growth, let's let x be the constant, but this time it's going to be a constant growth factor, right? Not a growth amount, but a growth factor. Remember, in the linear growth, we were adding x each time. Here you're going to see a little different story happening. So initial, well, that's not how you spell initial. So the initial number of lily pads is 2. Now, watch this. Let's say now the number after day 1, right? Because these guys are growing over the course of a week, and lily pads do grow really quickly, actually. So after day 1, it's 2 times x, right? Because whatever amount you had on day 1, you multiply by the constant factor to get the amount, whatever you had initially, you multiply by x to get the amount that you have left after day 1. Okay, and then likewise, the amount left after day 2 is 2 times x, otherwise known as 2x squared. Now watch the pattern here. Day 3 is 2x cubed because, for example, whatever you have on day 2, that gets multiplied by x to produce whatever you're going to have at the end of day 3, right? And then day 4, well, it's 2x to the 4th, right? It's another multiplication of the constant growth factor. Day 5 is equal to 2x to the 5th. Day 6 is equal to 2x to the 6th. And on the 7th day, day 7, it's 2x to the 7th lily pads. Now, if you think about it, what we have here that I'm going to highlight in green, what we have here are the algebraic representations of the amounts of lily pads that are present each day. And, you know, on these tests, like the GRE and the GMAT, a lot of times we have to equate in sort of an esoteric algebraic structure with a numerical value. And that's what we're going to do here. We know at the end of the week, the end of the 7 days, right, at the end of the week, there are 256 lily pads. And we know that this structure right here represents, you guys may have to scroll down as you know and see this. This structure here represents the number of lily pads at the end of day 7. So what we can say is, well, the algebraic number at the end of day 7 must equal the actual amount at the end of day 7. Divide by 2, we have x to the 7th equals 128. And we don't need any fancy math here like logs or exponents to do this. We can just ask ourselves what raised to the 7th power is equal to 128. And of course, the answer here is 2. X is equal to 2. Okay, so what that means is the constant growth factor is 2, which is a really high constant growth factor, right? Because it means the population is increasing by a factor of 2 every day. And just to give you a fun puzzle you can think about after the lesson, some of you may know the answer, but just to illustrate exponential growth, so I'll give you 2 options. Here's option 1, here's option 2. Option 1 is you can have $1 million today, or option 2 is you can start with 1 cent and some rich person will double your 1 cent each day for 30 days. Right? So for your first option is you can either have the $1 million, you can take the $1 million and walk away, no questions asked. Or option 2 is you can start with 1 cent, 1 penny, and you can double the penny every day. You have a rich benefactor. They're going to double your penny for you every day for 30 days. The question is, which option would you make out better with? You can play around with that on your own. Interesting. Okay, that was some exponential growth goodness. And now let's play around a little bit with some problems that require us to deal with word problems that integrate in fractions, but not the type of fractions that you did with Jeff, kind of a different spin. So let's give this guy a whirl. It's a pretty tricky problem, but try and make it simple. Try and eliminate all of the noise and confusion and get to the heart of the matter as quickly as possible. And we'll try for about 2 minutes starting now. Maybe a little longer, 2.5 minutes. All right, guys, let's see how we did on this. So it says the denominator of a certain fraction is 2 more than 3 times the numerator. So let's let x equal the numerator, and in case we need it, we'll let f equal the original fraction. So we're going to see there's going to be a change to the fraction here. It says if 7 were added to both the numerator and the denominator. And you know what, guys? I read over this every time, and I always say I'm going to make a comment about it, but for some reason I forget. So be careful in the GMAT. This is about verbal, right? Sentence correction. A lot of times students in private lessons will say, why are you saying were if 7 were? They say, isn't it 7 was? And the answer is no. In edited American English, this weird thing called the subjunctive mood dictates whether we say was or were. And when we're talking about a hypothetical situation, we use the word were. So if you always remember sort of the old classic phrase, if I were a king, I'd be rich, you'll be able to recognize this. Okay, so we would say if 7 were added, not if 7 was added. At any rate, take that for what it's worth. Okay, so 7 were added to both the numerator and the denominator of the fraction. The new fraction would be equal to 3/5. Okay, so if you think about it, so the denominator is 2 more than 3 times the numerator. Okay, well, if the numerator is x, and if the denominator is 2 more than 3 times, well, it's equal to 3x plus 2, right? And what I'm referring to here is the original fraction, and I'm just kind of literally decoding this area in green. If the denominator of a certain fraction, it says the denominator of a certain fraction is 2 more than 3 times the numerator. Okay, so what this gives us is the value of the original fraction. And we probably don't need f here, but just for clarity's sake, I'm going to put it in there and keep it. So it says 7 were added to both the numerator and denominator of the fraction. The new fraction would be 3/5. Well, that's pretty easy, right? So we're just going to add 7 to the numerator, and we're going to add 7 to the denominator. And if we do that, the fraction becomes 3/5. So this is kind of like the new fraction after we play around with it and add the 7 to the top and the bottom. Okay, so this is x plus 7 over 3x plus 9 is equal to 3/5. Let's cross multiply, so this will be 5x plus 35 is equal to 9x plus 27. Shuffle these around, combine like terms. What's that? 4x is equal to 35 minus 27 is 8. So so x is equal to 2. Okay, so we use the information about the new fraction to actually backtrack and figure out what the old fraction is. So x is 2, this is 3 times 2 plus 2, actually, plus 2. So this is what? This is 2 over 8, which is the same thing as 1 over 4. Okay, so the answer here looks like it's A. The original fraction is 1/4. Now, could you have back solved or plugged to do a ton of other stuff? Yeah, you could have, but, and you know what, guys, this is an important point that we can kind of end on that will give you some good strategy, not only if you're practicing, but on your test. You know, the test will never know why you got an answer correct. So if you plug, if you back solve, if you choose strategic numbers, if you pick C every time and 1/5 of the time you're right, it's never going to know whether you actually did the work correctly or not. Okay? So whatever is going to get you a good score, I encourage you to do. Here's the thing. If you're plugging, if you're back solving, if you're doing all that stuff in your practice, you're not learning anything. So you're learning like 2 skills, which are then you're trying to apply to a whole broad range of different scenarios. which if that's what you got to do, that's what you got to do. But in your practice, you may as well learn some actual skills that can actually be applied to a whole range, a whole barrage of different situations. And that's how you're going to be prepared, and that's how you're going to be confident and comfortable and fast. Right? There's nothing fast about back solving or plugging numbers. In fact, it's a real pain in the ass, excuse my language, right? But again, even if you practice with both methods, I think that's good, right? If you really love back solving and plugging numbers, do that. But at the same time, try and do the problem the right way, and you will find that it's amazing how quickly you build your math muscles. Right? It's like going to the gym to do pull-ups and having someone holding your legs the whole time. I think you guys know what I'm talking about. Someone can hold your legs so it's easier to actually pull your body weight up. Well, if you do that, that's fine, but how strong can you get? And it's the same thing here. So anyway, guys, I hope you enjoyed the webinar. If you're not using our curriculum now, I encourage you to get it. It's going to be a total game changer for you. And if you have any questions, please send Jeff or me an email. Jeff, any final questions?
No.
Okay.
Thanks for coming, everyone. We will see you next week.
See you next week, guys. Thanks a lot. Hope this is helpful for you.